Welcome to Cisco HyperFlex video series. This is regular cluster resiliency. When we talk about the HyperFlex data platform, we are talking about a hyperconverged solution which utilizes its distributed file system to provide maximum performance while maintaining resiliency with minimum performance impact even during failures. To show what this means in practice, we will perform a few failure tests and explain what happens, so that you can see the actual performance in practice. During the initial installation of the cluster, we had an option to choose the replication factor of the data platform, and we have chosen 3, which is the recommended option. This means that we have 3 copies of every block of information stored on the data stores at any given moment under normal circumstances. This replication factor has very real consequences on the failure tolerance of the cluster, since it defines how many data elements can be lost before the system goes offline. With the replication factor of 2, you can lose 1 full node for the system to remain operational. With replication factor of 3 and cluster size below 5, you can lose 1 node or 2 disks across 2 nodes for the system to remain operational. When you use the replication factor of 3 in a 5 or more node cluster, you reach the maximum resilience of 2 full nodes. So now we know what should happen. Let's show how this works on a real cluster. Here is the cluster we will perform tests on. And during tests, we will be copying this 900 GB file within the system to see if performance is affected. So we will have the VM window on the left and the HX Connect window on the right to show the failures that occur on the HyperFlex cluster in real time. The Windows VM we are using runs on the server 5 of our cluster and uses HX data store for storage. First, we will fail a drive on the server 5, where our VM is running. We are going to copy the file during this time. Now I have disconnected a capacity disk on the node 5. As you can see, the VM is still running normally. The reads are done from other 2 copies, while node 5 is still participating in writing. The cluster is now in unhealthy state though. It does not have the replication policy satisfied. Since we lost a disk, the blocks that were on that disk are not accessible anymore, and only 2 instances of those blocks exist on the cluster now. If we would wait for more than 1 minute, the system would already start a self-healing process after the removed drive failure. The self-healing process creates additional copies of the missing blocks from the copies that exist on the data store. Self-healing will recreate copies of the data that were lost on disk failure, and the replication policy of the cluster would be satisfied, returning the cluster to healthy state. We will reintroduce the capacity drive to the system before 1 minute expires, so the drive will be reintegrated into the system before self-healing starts. As you can see, it has not taken long for the drive to become available again, and the cluster to return to healthy state. The same resiliency applies to the caching drives as well. Now we will remove the caching drive on the same node and see what happens. As you can see from the copy graph, removing a caching drive again only mildly affects performance, and the Windows VM running on the node is still working normally. This is because nodes take over the caching. The IOVisor will not choose a node with a failed caching drive to cache data. We will reintroduce the caching drive and wait for it to become available. here. The system is now again healthy, and node 5 is now providing caching for the entire cluster. The local VM does not need either the local storage or the local cache. There is also another type of drive in HyperFlex nodes. This is the housekeeping drive. Since the CVM relies on this drive, losing it will cause the node to be marked as failed. Let's see. I have removed the housekeeping drive from the chassis. And as we predicted, the node is marked as inactive. But the VM on it runs normally. This is because reads and writes are done exclusively across the network now. The IO-visor forwards all the requests to other nodes, which allows the VM to run without moving. When we reconnect the drives, the system reestablishes itself. This takes a little longer. So the VM is not reliant on local data to run, and the amount of failures that the system can sustain is limited by the replication factor. To demonstrate this, we will fail an entire node by disconnecting the cables on the fabric interconnects. This will isolate a node as if it was powered off. To make things worse, we will disconnect the nodes from the currently used fabric first, so that the networking will be forced to fail over for all the nodes. We will disable the nodes 1 and 2. As you can see, the node failure caused an intermittent disconnect even though the node we are using was not on the host we disabled. This is because all the servers failed over to the other fabric and are now communicating through the secondary fabric interconnect. Now we will fail the second node. We have reached the maximum number of allowed failures for the replication factor of 3 on a 5+ node cluster. If any more failures happen, the HyperFlex system will go offline. This does not mean that all the information on the entire system is lost, but the system operations will stop. We could further extend the number of failures that could be sustained on clusters of 8 or more converged nodes, by using logical availability zones, or LAZ for short. This feature can be enabled while the cluster is already operational, and it will rearrange the data on the cluster so that the servers will be rearranged into zones. Now with the replication factor 3, the information is stored on the HyperFlex data platform in such a way that any amount of servers can fail, as long as they are all from no more than 2 zones, and the system remains operational. Once you lose an additional server in the 3rd zone, the system will go down. The LAZ is also a solution which does not use up more space on the storage and just rearranges the data differently, improving your resilience of bigger deployments even further. This was regular cluster resiliency. Thank you for watching.